SpaceX Starship Flight Number 10 utilizes a significantly evolved vehicle stack compared to its predecessors. The complete stack measures 124.4 meters in height, a 3.1 meter increase over Block 1 configurations with enlarged propellant capacity and structural modifications of the Block 2 design, the total propellant load reaching 5,150 metric tons distributed between the booster's 3,650 ton capacity and the ship's 1,500 ton load. The selection of Ship 36 and Booster 16 for this mission is a calculated engineering decision. Ship 36 incorporates the full suite of Block 2 improvements, while Booster 16 benefits from manufacturing refinements developed through the production of its predecessors. Both vehicles have undergone comprehensive ground testing, with Booster 16 completing a full-duration 33 engine static fire test on June 6th, demonstrating 7,590 tons force of thrust for 8 seconds, a critical validation of the integrated propulsion system. The path to Flight 10's launch readiness has involved extensive component and integrated systems testing. Ship 36's single-engine static fire test on June 16th validated the redesigned propellant feed systems and engine mounting interfaces. These tests, conducted at Starbase's Massey's test site, have provided critical data on the Block 2 designed structural response to thrust loads and acoustic environments. Beyond propulsion testing, both vehicles have undergone comprehensive avionics validation, thermal protection system inspection, and structural proof testing. The enhanced pre-flight campaign reflects lessons learned from Flight 9, where post-flight analysis revealed that certain failure modes could have been detected through more comprehensive ground testing protocols. The thermal protection system, TPS, on Ship 36 is perhaps the most visible evolution in Block 2 technology. The system comprises approximately 18,000 hexagonal ceramic tiles, each measuring 9.5 inches across with a thickness of 0.033 meters. This standardized geometry allows for efficient manufacturing and installation while providing comprehensive coverage of the vehicle's heat-exposed surfaces. The tile composition itself has evolved significantly from earlier iterations. The current design utilizes a silica-based ceramic substrate, enhanced with toughened unipiece fibrous insulation coating. This combination provides exceptional thermal resistance, with tiles capable of withstanding sustained temperatures up to 1,377 degrees Celsius or 2,510 degrees Fahrenheit. The addition of molybdenum disilicide coating on the outer surface enhances oxidation resistance and provides the characteristic appearance of the heat shield. Perhaps the most critical improvement in Flight 10's TPS is the transition from adhesive bonding to mechanical fastening systems. This fundamental change addresses the tile shedding issues observed in previous flights where adhesive degradation under thermal cycling and acoustic loads led to tile loss during ascent and re-entry phases. The mechanical attachment system employs a 3-point mounting configuration with spring-loaded pins that accommodate thermal expansion while maintaining positive retention. Each tile incorporates a backing structure that distributes loads across the vehicle's skin, preventing stress concentrations that could lead to structural failure. This design allows for individual tile replacement without affecting adjacent tiles, which is a critical maintenance consideration for rapid reusability. Beneath the primary tile layer, Flight 10 incorporates a based secondary thermal barrier. This felt-like material provides additional insulation and serves as a backup protection layer should primary tiles fail. The material's ability to char and ablate under extreme heating provides a sacrificial protective mechanism, buying critical time for vehicle survival during off-nominal re-entry conditions. SpaceX has also integrated experimental metal heat tiles in select locations on Ship 36. These aluminum-based tiles, while heavier than their ceramic counterparts, offer potential advantages in durability and thermal conductivity management. Their inclusion on Flight 10 is a controlled experiment in alternative TPS technologies that could inform future design iterations. The Block 2 design implements significant changes to aerodynamic control surfaces that directly impact thermal protection requirements. The forward flaps have been repositioned more leeward and reduced in size, decreasing their exposure to peak heating during re-entry. This modification, while requiring adjustments to flight control algorithms, substantially reduces the thermal load on these critical control surfaces. The aft flaps retain their original sizing, but benefit from improved hinge designs that better manage thermal expansion and provide enhanced sealing against hot gas ingestion. These design changes reflect a holistic approach to thermal management that considers not just surface heating, but also the complex interactions between vehicle geometry and re-entry plasma dynamics. Flight 10's propulsion system centers on the proven Raptor 2 engine architecture, with 33 engines powering Booster 16 and 6 engines, 3 sea-level and 3 vacuum-optimized variants, on Ship 36. Each sea-level Raptor 2 generates 230 metric tons force at sea-level conditions, while the vacuum variants produce 258 tons force, achieving this performance with a mass of just 1,630 kilograms, which is a 21% reduction from the original Raptor design. The engines operate at a chamber pressure of 300 bars, and this extreme operating condition enables specific impulse values of approximately 350 seconds at sea level and 380 seconds for vacuum operation, representing near theoretical performance for the Methalox propellant combination. A notable milestone for Flight 10 is the inclusion of SpaceX's first refurbished Raptor engine. One of Booster 16's engines previously flew on Flight 5's successful booster catch mission. This refurbished engine underwent comprehensive inspection and testing, including hot fire validation, before integration into the Flight 10 vehicle. The engine reuse program has revealed valuable insights into wear patterns and degradation mechanisms. Post-flight analysis of recovered engines has shown that primary wear occurs in the turbo pump assemblies and combustion chamber throat regions, leading to targeted improvements in materials and coatings for these high-stress components. Flight 10 incorporates substantial improvements in propellant management systems, directly addressing the failures observed in Flight 9. The implementation of vacuum-jacketed feed lines is a 25% reduction in cryogenic boil-off rates, extending the vehicle's orbital loiter capability and improving propellant availability for landing burns. The header tank system, critical for landing propellant supply, has been completely redesigned for Block 2. The new configuration features improved slosh baffles, enhanced pressurization systems, and redundant level sensors that provide real-time propellant quantity data to the flight computers. These improvements ensure consistent propellant delivery during the dynamic maneuvering required for landing operations. The engine management system for Flight 10 features enhanced startup reliability software, specifically developed for landing burn conditions. This software accounts for the unique challenges of relighting engines in a low-gravity, potentially propellant-depleted environment. The system implements predictive algorithms that adjust ignition timing and propellant flow rates based on real-time sensor data, improving the probability of successful engine restart. The gimbal control system maintains the proven 15-degree range of motion, but incorporates higher precision actuators and improved position feedback sensors. These enhancements enable more precise thrust vector control, critical for maintaining vehicle stability during the complex flip maneuver and landing burn sequence. The Block 2 avionics architecture is a comprehensive redesign of Starship's nervous system. The new flight computers provide substantially more processing power than their predecessors, enabling complex mission profiles and real-time trajectory optimization. The system operates on a triple redundant architecture with automatic failover capabilities, ensuring continued operation even with multiple component failures. The main flight computers operate at a 10 Hz update rate for primary control loops, with critical subsystems running at up to 50 Hz. This high-frequency operation enables precise control during dynamic flight phases and provides the computational headroom necessary for advanced guidance algorithms. Flight 10's communication architecture integrates Starlink, GNSS and traditional RF systems into unified antenna arrays. This integration reduces the vehicle's antenna farm complexity while providing multiple independent communication paths. The Starlink integration is particularly significant, offering high-bandwidth telemetry downlink capabilities that enable real-time streaming of comprehensive vehicle health data. The navigation system combines inertial measurement units with star trackers and GNSS receivers to provide precise position and attitude determination. The star tracker integration is a new capability for Starship, enabling accurate attitude determination during coast phases when GNSS signals may be unavailable or unreliable. The vehicle's electrical system centers on a 2.7 megawatt distributed power architecture. This system must manage the demands of 24 high-voltage actuators, comprehensive sensor suites, and communications systems while maintaining sufficient reserves for contingency operations. The power system employs smart battery management with integrated health monitoring and predictive failure detection capabilities. Solar panel deployment mechanisms have been tested on Ship 36, though they will not be activated during Flight 10. These panels, when operational on future flights, will provide supplementary power for extended missions and reduce battery depth of discharge during coast phases. Flight 10 carries over 30 cameras distributed across both vehicles, providing comprehensive visual coverage of all critical events. These cameras serve multiple purposes: engineering data collection, public outreach, and real-time anomaly detection. The video processing system can automatically flag unusual events for priority downlink, ensuring critical data preservation even in communication-constrained scenarios. Beyond cameras, the vehicle incorporates hundreds of pressure, temperature, strain, and acceleration sensors. The data management system must process, prioritize, and store this information while selecting critical subsets for real-time downlink. This hierarchical data management approach ensures that mission-critical information receives priority, while preserving comprehensive datasets for post-flight analysis. Flight 10 will follow a trajectory similar to its predecessors, launching from Starbase's orbital launch mount on a bearing that takes it over the Gulf of Mexico. The initial ascent phase will stress the integrated stack to its maximum aerodynamic loads, providing critical data on the Block 2 structural modifications. The hot staging maneuver, where Ship 36 ignites its engines before separation from Booster 16, is one of the most dynamic events in the flight profile. The Block 2 design incorporates reinforced staging interfaces and improved venting systems to manage the extreme thermal and acoustic environments during this critical phase. Following separation, Booster 16 will execute a complex return profile aimed at demonstrating the tower catch capability. The booster must perform a boost back burn to reverse its trajectory, followed by atmospheric entry and a precise landing burn that positions it between the tower's chopstick arms. The catch attempt on a booster's maiden flight is an aggressive approach to vehicle validation, and success would mark only the second successful tower catch and the first for a Block 2 booster configuration. During the coast phase, Ship 36 will attempt several critical demonstrations. The payload bay doors must open successfully to deploy 8 Starlink satellite simulators, a capability that failed on Flight 9 due to actuator malfunctions. These simulators, while non-functional, replicate the mass and deployment characteristics of operational Starlink 5-3 satellites. The coast phase also provides the opportunity for the mission's most critical objective, in-space Raptor engine relight. This capability is essential for orbital operations as it enables orbit adjustments, deorbit burns, and eventual interplanetary transfers. The relight attempt will test the engine's ability to start in a zero-gravity environment with potentially degraded propellant conditions. The re-entry phase will test the full suite of Block 2 improvements under the most demanding conditions. Ship 36 must maintain attitude control while managing the extreme thermal loads of atmospheric interface. The repositioned forward flaps and enhanced heat shield are designed to provide improved control authority while reducing thermal stress on critical components. The flight will conclude with a targeted splashdown in the Indian Ocean, approximately 65 minutes after launch. While recovery is not planned for this mission, the controlled nature of the re-entry and splashdown provides valuable data on vehicle condition and performance throughout the flight envelope. SpaceX has established 5 critical success criteria for Flight 10, each addressing specific technical capabilities required for operational status, in-space engine relight. Successful restart of at least one Raptor engine during the coast phase, demonstrating the capability for orbital maneuvering and deorbit burns. Payload deployment, successful opening of payload bay doors and deployment of all 8 Starlink simulators, validating the mechanical systems required for operational satellite delivery. Attitude control maintenance, sustained vehicle control throughout all flight phases, particularly during coast and re-entry, addressing Flight 9's loss of control failure. Heat shield performance, successful protection of the vehicle through peak heating, validating the Block 2 thermal protection system improvements. Booster recovery, successful catch of Booster 16 by the launch tower, demonstrating rapid reusability capability for the Super Heavy first stage. Beyond the primary objectives, SpaceX will evaluate numerous secondary metrics that inform future design iterations. Propellant system integrity, a measurement of leak rates and pressure maintenance throughout the mission, particularly during coast phase. structural response, evaluation of vehicle structural dynamics under flight loads, validating design margins, and identifying areas for mass reduction. Avionics performance, assessment of the new flight computer architecture's performance under actual flight conditions. Thermal management, detailed analysis of heat flux distribution and thermal protection system response across the vehicle surface. Flight 9's May 27th, mission achieved several important milestones while revealing critical design vulnerabilities. The successful reuse of Booster 14 marked a historic first, demonstrating the fundamental viability of super heavy reusability. The achievement of second engine cutoff represented the first time a Block 2 ship reached orbital velocity, validating the basic propulsion and structural design. However, the mission's failures provided equally valuable data. The propellant system leaks that developed during coast phase led to a cascade of failures: loss of main tank pressurization, depletion of attitude control propellant, and eventual loss of vehicle control. Post-flight analysis revealed that thermal cycling and structural loads during ascent had compromised several propellant system joints, leading to progressive leakage throughout the coast phase. Flight 10 incorporates comprehensive design changes to address Flight 9's failures. Enhanced joint design, all propellant system joints now feature increased preload and redundant sealing surfaces. Critical connections employ self-energizing seals that increase sealing pressure in response to internal pressure, providing improved leak resistance. New purge systems maintain positive pressure in critical areas, preventing propellant vapor accumulation and reducing the risk of combustion in the event of minor leaks. Redundant attitude control. The reaction control system now features multiple independent propellant supplies and cross-feed capabilities, ensuring attitude control capability even with significant primary system degradation. Improved diagnostics. Enhanced leak detection systems provide real-time monitoring of propellant system integrity, enabling proactive responses to developing issues. The Block 2 design implemented in Flight 10 is a 25% increase in propellant capacity compared to earlier configurations. This increase comes not from larger tanks, but from improved packaging efficiency and reduced structural mass. The use of advanced manufacturing techniques, including friction stir welding and automated fiber placement, has enabled thinner wall sections while maintaining required strength margins. The landing leg deletion on Ship 36, following SpaceX's commitment to tower catches for ship recovery, saves approximately 5 tons of mass. This mass savings translates directly into increased payload capacity or extended mission duration, demonstrating the compound benefits of the catch recovery approach. While Flight 9's heat shield performed adequately during its uncontrolled re-entry, the lack of attitude control prevented collection of controlled re-entry data. Flight 10's enhanced TPS, combined with improved attitude control capabilities, promises to provide the first comprehensive dataset on Block 2 thermal protection performance under controlled conditions. The transition from adhesive to mechanical tile attachment is a fundamental reliability improvement. Flight 9 lost an estimated 150 tiles during ascent, while ground testing of the Flight 10 configuration has shown virtually no tile loss under equivalent conditions. The propulsion system improvements between flights extend beyond the previously discussed enhancements. The implementation of improved LOX filtration systems addresses turbopump contamination issues observed in recovered Flight 9 engines. These filters, positioned upstream of the turbopump inlets, capture debris that could otherwise cause catastrophic pump failure. The engine controller software has been updated to better handle off-nominal conditions. Flight 9 telemetry revealed several instances of marginal combustion stability that, while not causing immediate failure, indicated operation closer to stability limits than desired. Flight 10's updated control algorithms provide increased margin through active combustion monitoring and adjustment. Success in Flight 10's objectives would unlock several critical capabilities for the Starship program. In-space engine relight enables true orbital missions, potentially as soon as Flight 11. Successful payload deployment demonstrates readiness for commercial Starlink launches, providing revenue generation to support continued development. The Block 2 configuration tested on Flight 10 is the baseline for near-term operational missions. However, SpaceX continues aggressive development of Block 3 improvements, including Raptor 3 engines, promising 22% greater thrust and further mass reductions through integrated design approaches. The path from Flight 10 to operational status requires demonstration of several additional capabilities. Orbital propellant transfer, critical for lunar and Mars missions, requiring precise attitude control and specialized plumbing interfaces. Extended duration flight, demonstration of multi-day orbital operations, validating life support systems, and long-term propellant storage. Crew capability, integration and testing of life support systems, crew interfaces, and abort capabilities required for human flight certification. High-energy re-entry, validation of TPS performance under lunar and interplanetary return conditions, requiring velocities substantially higher than low Earth orbit. Flight 10's technical objectives align directly with SpaceX's broader strategic goals. The rapid reusability, demonstrated by tower catches, enables the high flight rates necessary for Starlink constellation deployment and iterative vehicle development. The payload capacity unlocked by Block 2 improvements positions Starship as a compelling option for large satellite deployment and space station logistics. Perhaps most significantly, successful demonstration of in-space relight and controlled re-entry validates the fundamental architecture required for Mars missions. The mission's aggressive objectives, including attempting a tower catch on Booster 16's maiden flight and demonstrating critical in-space capabilities, embody SpaceX's philosophy of pushing boundaries while learning from each attempt. The technical data gathered from Flight 10, whether in complete success or partial achievement of objectives, will inform the rapid iteration of Starship